Okay, so the plan for today was to go through sort of something that looks pretty damn close to what was in the second test, I think it is. So let's just have a look at this. This was a question that is actually like not too difficult, but a lot of people did a lot more work than what needed to be done. So it says here, what contains the greatest mass of oxygen? 0.75 moles of ethanol, and then it gives the formula, 0.6 moles of formic acid, and it gives the formula, or 1 mole of water. And so the key thing here is that the thing that contains the greatest mass of oxygen also contains the greatest moles of oxygen. So the quickest way of solving this is to figure out how many moles of oxygen are present in each case. So for ethanol, we see that we get from the formula 1 mole of oxygen for every 1 mole of ethanol. So if I've got 0.75 moles of ethanol, then what that means is that I've got 0.75 mole of oxygen. So I'm sort of a third there, third of the way down. Now it says, what if I've got 0.6 moles of formic acid? And the key thing here is in formic acid, you get 2 moles of oxygen for every 1 mole of formic acid. So 2 moles of oxygen for 1 mole, and I'm just going to call it Fa. Here we go. And so now I've got 0.6 mole of Fa. So 0.6 times 2, I've got 1.2 mole of oxygen, okay? So this is looking like it's got more. So if I was running out of time, I could kind of stop at this point and just go, okay, I'm gonna guess formic acid. But let's move on and do it for water. And it says that I have 1 mole of water. So I know that I get 1 mole of oxygen for every 1 mole of water, and I've got 1 mole of water, and there we go. So that would mean that I would get 1 mole of oxygen. So it's obviously got to be the formic acid. The question though, you do want to be aware that it says explain why. A good way of avoiding actually using your words here to explain why is you can just do the math like I did, or but the answer is formic acid as the 2 moles of O for every 1 mole of formic acid. So that's the reason why you just have a greater mole ratio of oxygen in formic acid. Ethanol, you only get 1 mole of oxygen per mole of ethanol. Water, you only get 1 mole of oxygen per mole of water. Formic acid, you get 2. So hopefully that makes sense. And yeah, hopefully you were able to follow along with that. Okay. This next one here is an interesting problem. I'm just going to move the camera up just a tiny little bit because it looks really kind of complicated. And remember, you can follow along if this is a little bit too blurry. You can follow along online. You can follow along with the document that I sent you. So it says, what is the mass of solute in half a liter of 0.3 mole per liter? And that's glucose is the formula there. And the molar mass is 180.16 grams per mole. And this is really easy. You just need to memorize the little formula for the mass of solute. And I'll show it to you now. It is the mass of solute is equal to the concentration times the volume times the molar mass. So if I put my units in, you'll see that this works. The concentration is 0.3 moles per liter. My volume is half a liter, and then my molar mass was 180.16 grams per mole. And you can see that liters cancels, moles cancels, and leaves me with grams, which is what I want. And so I'll just put that into my calculator now, and you'll see how easy this is. So 0.3 times 0.5 times 180.16, and that ends up being 27.02. So I should probably go through and check my sig figs here, and the sig figs are going to be limited by this guy, 0.3 grams. So my actual answer there should be rounded off to 2 sig figs, which will be 27 grams. Okay, so I hope that makes sense. So it's really just, being aware of this little formula. You can use your units to make certain that you've recalled the formula correctly. So I think a lot of people, again, kind of did a whole bunch of math here that really isn't needed for these types of problems. Okay. All right, we'll whizzing through it here. So it says, an experiment in the general chemistry lab calls for 2 moles, calls for a 2 mole per liter solution of hydrochloric acid. How many milliliters of 11.9 mole per liter hydrochloric acid would be required to make 250 milliliters of 2 mole per liter hydrochloric acid? So you have to recognize that this is a dilution problem. So we're going to use the dilution formula, and we need to know how many milliliters of the concentrated stuff. So the dilution formula is C1V1 equals C2V2. The 1 refers to the concentrated stuff and the 2 to the dilute. So the more concentrated one is 11. Well, let's do our algebra first of all. What we're trying to solve for is how many milliliters of the more concentrated thing. So we're trying to solve for the volume 1, okay? So we can just do this algebra now. V1 equals C2 on C1, okay? So it's not a bad thing to do the algebra with the symbols first. I was about to start doing the numbers and I kind of had to stop myself. So V1, C2 is my more dilute one, so that is 2 moles per liter. And I'm just going to use the symbol uppercase M to indicate molarity. I often do that when I'm doing a dilution problem. Times, and then V2 is the volume of the dilute side, which is that 250 milliliters there. And then C1 is my more concentrated volume, and that's 11.9 moles per liter. And so you can see that my moles per liter cancels out and leaves me with milliliters. Now, it should be a number that is less than 250 because I'm going to take a little bit of the concentrated stuff and dilute it down until I have 250 milliliters. So how much do I need? I need 42.02 milliliters. Now I'm just going to check my sig figs. 3 sig figs for this concentration, 3 sig figs for this concentration, 2 sig figs for this volume, 3 sig figs for this one. So I want my answer to 2 significant figures, and so I need 42 milliliters of the concentrated stuff when I do the math there. So looking at this problem, I think a good strategy here is I recognize that it's a dilution one. So it's going to be using the dilution formula, C1V1 equals C2V2. I know that side 1 is where all the more concentrated stuff is. Side 2 is where the dilute stuff is. I want to know how many milliliters of the more concentrated solution. So I do my algebra, and then I put my numbers in with my units, cancel out my units, and then compute my answer. And then I just double checked my sig figs and wrote it to the correct sig fig. So there's quite a bit going on there, but not impossible. That problem was a real mixed bag, and some people had memorized the dilution formula, they had it written out, but they didn't know how to use it, and they didn't know what the variables were referring to. Michael just asked, what was the number in the problem that had two significant figures? And it's the 250 milliliters here, because the trailing zero doesn't count because there's no decimal point in that number. So trailing zeros only count if there is a decimal number. So therefore, this number here has two significant figures. Does that help, Michael? Yeah, Michael, you got it. All right. So this is a sort of it's a different type of problem here. It says, what mass of hydrogen chloride is contained in 45 milliliters of an aqueous solution that has a density of 1.19 grams per mil and contains 37.21% hydrogen chloride by mass. So what's going on with this problem is you're being asked to use density as a conversion factor between volume and mass, and then you're being asked to use percentage as a conversion factor. So it's really a dimensional analysis problem. So what we're trying to do is we're going to start with 45.0 milliliters. And where we want to end up is, it says, what is the mass of hydrogen chloride? We want to end up in grams of HCl. Okay, so 45 mils of the solution, we know that the solution has a density. You get 1.19 grams of the solution for every 1 milliliter. So that's the first part. But that would only give me the grams of the solution. What I want is the grams of the hydrogen chloride. And what I have to recognize is that the percentage is indicating the number of grams of hydrogen chloride in 100 grams of the solution. And that's the secret here. So I get 37.21 grams of HCl for every 100 grams of the solution. And so now I'll multiply those two things together, and you'll see what I get. So 45 times 1.19 times 37.21 on 100, and only part of it should be hydrochloric acid, right? So we'll see what we get for that. So it should be a number that is, you know, less than 45. So I ended up getting 19.93. I want to check my significant figures here. It's this guy's got 3 sig figs, this guy's got 3 sig figs, this one's got 4, so I want 3 sig figs. So it's going to be 19.9 grams. So I'm just going to go back and answer Michael's question, which was about the previous one. And it was, why does this number here, 250 milliliters, have two significant figures? So the number that is written is 250, and our rule is that any non-zero number is significant, so those two are significant, and then trailing zeros at the end of a number are only significant if the number has a decimal point. This number doesn't have a decimal point, so that means that that guy is two significant figures. So that's what's going on there. Now, if there was a decimal point there, then that would become 3 sig figs, because now the trailing zero would count. If there was a decimal point and then another 2 significant figures, then that would be 5 significant figures. So I hope that that helps clarify some of that. So problems that involved both the density and the percentage were kind of a little sketchy for many people. So there are a few problems that were assigned in from the book that are of this type. So if you can recognize those and perhaps look in the answer key to see how people work them out, then that might be a beneficial thing to do. Okay, so this was one that was kind of a mixed bag. Again, I think it's something that I might have a little bit of trouble kind of making it large enough for you to see clearly. So again, if you want to, you can kind of follow along on that document that I attached to that announcement this morning. It's just going to be a little blurry on the text there, and I may not be able to write with my big pen. So we'll see how we go. But I'm going to have to zoom out a little bit to fit everything in. Okay, so it says, from the balanced molecular equations, write the complete ionic and net ionic equations for the following. So what we're really looking for here is any aqueous ionic compounds will be completely dissociated. Any strong acids will get completely dissociated. Any solids will not be written in their dissociated form. Any weak acids won't be written in their dissociated form. And any covalent compounds that are not acids won't be written in their dissociated form. So a complete ionic equation includes all of the spectator ions, and the net ionic equation is what we get when we eliminate the spectator ions. So we'll just go through and kind of basically expand each of these out to get the complete ionic. So for A, the lead 2 nitrate here is aqueous, so I'm going to break that apart. And I do have to have my phase labels for this to make sense. And then I get 2 nitrates. And this is where I was kind of worrying about using my big pen. And then I have to break this as a strong acid. So it's going to give me 2 hydrogen ions. And then here's a sulfate like so. Okay, so that's the left-hand side of that guy. I'm going to do this kind of vertically. And so now what does it come together to form? The lead 2 sulfate is a solid. So I'm going to leave that guy intact. And then the nitric acid here, that's a strong acid. So that guy dissociates into ions. So a little bit of help here is to recognize that you don't ever break apart polyatomic ions. You leave them together. That's a common error. And then you can use the number of hydrogen ions that are formed when an acid dissolves to get the charge on the polyatomic ion if you're a little sketchy on that. All right, so that's the first part. Now, how am I going to get my net ionic equation? I'm going to cancel out any spectator ions, and they're ions that appear in the same form on both sides of the arrow. So in my case, that's going to be these nitrate anions, and then it's going to be these 2 hydrogen ions here. So when I do that, I get a net ionic equation, Pb2 plus Aq plus SO4 2 minus Aq gives me Pb SO4 solid. So I might just make that really clear that that's like that. All right. So again, a real mixed bag on people's performance on this. It wasn't like spectacular, I hate to say. It was kind of a little weird. I'm just going to grab I'm just going to cover this over now, and so that I have space to do the next one. All right. So in B, it's the same thing again. I'm keeping an eye out for covalent molecules, weak acids, and solids. I'm not going to dissociate those. And I am going to dissociate strong acids and aqueous ionic compounds. All right, so this makes it a little easier. So CaCO3 is a solid. H2SO4 is a strong acid, so I get 2 hydrogen ions and a sulfate anion, and that's my left-hand side. I'm going to go vertically again because I'm trying to use this nice fat pen so you can see easily. And then the calcium sulfate is a solid, so I'm going to leave that intact. And then CO2 gas, that's a covalent molecule. There's no metal present there, so I'm going to leave that intact. And then water is a covalent molecule, so I'm going to leave that intact. So what's weird about this one, or nice about it from your perspective, is that the complete ionic with all of the spectator ions in place and the net ionic are the same thing. There's no spectator ions to cancel. So at this point, we're done and we can move on. So that's kind of nice. All right, that makes it easy. Okay. Now, you've had a lot of practice, I think, sort of in homework, and we spent some time in class, and we worked on group quizzes together, writing acid-base reactions. And this one says write a balanced molecular equation for the following acid-base reactions. So that kind of keeps it nice and simple. We don't have to dissociate things. So we know that when an acid reacts with a base, so that it's going to form water and then an ionic compound. There's what we call a proton transfer reaction. So the challenge is always figuring out the ratio of the acid to base and the formula of the ionic compound. So let's write our acid and our base for the first one, then our arrow, and we know that one product will be water, and now we need to just figure out the formula for the ionic compound. So lithium is in group 1A, so it's +1. And then I know that this anion must be -1 because it combines with one hydrogen ion, which is a single positive charge, to make an acid. So it's got to be -1. So these guys have equal and opposite charges, so no need for the crossover rule, and they're just going to combine 1 to 1. Okay, so let's double check that it doesn't ask for phase labels or anything weird like that. No, that looks good. We can put the phase labels in if we want. They both are solutions. Water is a liquid, and because this is a group 1 compound, it will be soluble. Okay, so that's A. It's definitely a molecular equation and it's definitely balanced. Everything is 1 to 1. We like those ones, but it's too good to be true, right? Then it says an aqueous solution of H2SO4, so H2SO4 AQ reacts with sodium hydroxide, and anything that has sodium in it is always going to be AQ when there's water present. What does it form? It forms water, which is a liquid, and then an ionic compound, and we're going to have to figure out the formula of that ionic compound. So what I'm thinking is, let's do this like this, is okay, sodium, it's group 1, sulfate, SO4, must be 2- because they've got 2 hydrogens there. These are not equal and opposite, so I'm going to have to do crossover to get the formula, and then that means that it's going to be Na2SO4. So Na2SO4 is my formula there. I'm kind of moving on to a separate piece of paper because it's a bit awkward, but there we go. All right, so that doesn't really balance now because I've got 2 sodiums over here and I've only got 1 over here. So I'm going to need 2 of those. And then if you're observant, you'll see that the hydrogen ions don't balance either because I've got 4 hydrogens on this side and I've only got 2 over here. So I'm going to need a 2 in there. And then now everything looks good. 1 sulfate, 1 sulfate, 2 plus 2 gives me 4 hydrogens. 2 times 2 gives me 4 hydrogens. and then I've got 2 oxygens over here and 2 oxygens over there. So a little trickier on the second one there, but the real key is you've got to work to figure out what the formula is of that ionic compound. Okay, cool. Again, it was a mixed bag on this one. If people had, if people had it, they had it. If people didn't have it, they were just kind of like trying to BS their way through, and it kind of tended to go bad. So this is, it says balance the following equation according to the half reaction method. Show each of the steps clearly. So this is kind of, this is when you kind of take a deep breath and you kind of remember those 8 steps that we went through. This one is looking like it's going to be not too bad because it says it's in acid, and that really makes it a little easier because we don't have to do that final step of switching over to base. So our first step is to break this into half equations. So I'm going to write 1 half equation for each reactant, and I left a little bit of space there to add some stuff in. Then I need to write my products. So that's going to be Br minus, and that's going to be SO4 2 minus. Now I go ahead and I balance the atoms that are not oxygen. So here I've got 2 bromines on the left, but I've only got 1 bromine on the right. So I'm going to need a 2 there. And here I've got 1 sulfur on the left and 1 sulfur on the right, so it's already balanced. So what I've got to do once I've done that is to balance for oxygens by adding water. So there are no oxygens here and no oxygens here, so I'm good. There are 2 oxygens here and 4 oxygens here, so I'm going to be needing 2 waters in there. Once I've balanced for waters, I'm going to go through and balance for hydrogen atoms by adding H+. There are no hydrogen atoms up here, but down here I've got 4 2 times 2 hydrogen atoms on the left, so I'm going to need to add in 4 hydrogen atoms over here. And now I have to balance for charge by adding electrons. On this side, I've got 0 charge, and on this side, I've got 2 times -1. So total charge on this side is -2, and total charge over there is 0. So I'm going to need to add in 2 electrons. Now over here, I've got no charges, so total charge on that side is 0. And then over here, I've got 2 things that have charges. I've got a 2- there, and then I've got 4 1+ over here. So my total charge over here is 2+. So I have to get my 2+ back to 0 because I always add electrons to my more positive side. So I need 2 electrons over there. So now everything is balanced. I have to check that the electrons gained equals electrons lost. And if it doesn't, I would multiply. And the big mistake that I saw here is that people forgot to put the 2 out the front for the bromine there. In this case, because we've got 2 electrons being gained and 2 electrons being lost, we're ready to go ahead and add up everything up. So I always cancel my electrons first, and then I look to see if there's anything else to cancel. If my electrons don't cancel, I'm on the wrong track. So that looks good. There's nothing else there to cancel. No waters, no hydrogen ions. They're common things that get cancelled. You've just got to kind of make certain that everything gets copied down. And we're very happy because this one is in acid, so we don't have to convert to base, but we're just going to check everything at the end. And this is where I discover that I forgot to move those bromines down. You see 2 bromines there, and I don't have it written here. So I need to bring those guys down. And now that is good. See, I did that on purpose so you would see my error. Okay. And then now I can check my sulfurs. I've got 1 on the left and I've got 1 on the right. Now you can check my oxygens. I've got 2 here and then another 2, so that's 4. And then over here I've got 4, so that's good. Sulfurs, it's good too, if you cross that off. We've only got 1 more atom to check. Hydrogens, we've got 2 times 2, that's 4. And then we've got 4 over there, so that is good. And then finally, I want to look at my charge. So I've got no charges over here. And then I've got a bunch over here. I've got 2 minus and then another 2 minus, that's 4 minus, and then 4 pluses, so overall that's 0. Okay. All right, so it looks good. I'm like really confident. Once I added in those 2 bromides there, everything seemed to work out okay. All right, that was kind of a mixed bag. Some people were just like, it was a disaster, you know, like they just didn't know how to do it, and it was really bad. And then other people just were like done in like 2 seconds flat. So I would say that, you know, if you know the procedure, it's not hard, and there's a lot of spots along the way to check that you've got everything straight. All right. So this one was a little mean, but I didn't feel too bad about it. And I kind of considered not giving it to you. But I'm going to give you the hints now as to how to solve it. So the question is asking, classify the following as acid-base reactions or oxidation-reduction reactions. So acid-base reactions are what we call, another name for them would be proton transfer. And oxidation-reduction reactions are electron transfer. Okay, so a proton gets transferred from an acid to a base. That gives you an acid-base reaction. And electron transfer is, you know, it's harder to observe, but how we can tell that we've got electron transfer is that there will be a change in oxidation number. So a couple of characteristics of acid-base reactions. The first one is that there's always a transfer of a hydrogen ion, and there is no change in oxidation number. How we can, some characteristics of redox reactions. They're electron transfer. There are changes in oxidation number. And then here's the real thing that really helps you out here is any reaction involving an element. So any reaction involving an element automatically gets classified as redox. And I'll tell you why. When an atom is in an element, its ON is equal to 0. But when an atom is in a compound, the ON is never 0. So what that means is that when an atom moves from its elemental form to being in a compound, there is always a change in oxidation number. Or similarly, when an atom moves from being in a compound to being an element, there's always a change in oxidation number. So that can really help us recognize redox reactions. So I'm going to go up to the top here, and I'm going to look at these 3 reactions here and see, are there any that involve elements? And if there are, I'm going to immediately label those as redox. And you can see this guy involves 2 elements, so it automatically becomes a redox. Now, the one at the bottom here also involves 2 elements, magnesium and chlorine, so that automatically becomes redox. Now, the more difficult way of doing this would be to assign oxidation numbers to everything and see if anything changed, and I guarantee you it does. Now, A is a little more difficult because it doesn't have any elements in it. Now, if I assigned oxidation numbers to everything, and I'm not going to do that, what I would find is that none of them change. But the other thing that I can see here is, so that eliminates it from being a redox, but is that basically there's this sulfur, there's an exchange like this, right? There's proton transfer. So if I would go through and I would see that there is no change in oxidation number, that's powerful evidence for it being an acid base, but it also has to be proton transfer. So this one is acid base. Now, why I kind of thought that that question was slightly mean is because whenever I'm asking you to write an acid-base reaction, I told you that it always involved an acid reacting with a base to form water and a salt. And this is a little bit confusing because there's no water present. But I didn't feel too bad about it. Yeah, because the main reason I didn't feel too bad about it is because I had told you that for a redox reaction, there has to be a change in oxidation number. And in the first one, there is no change in oxidation number, which means it must be some other kind of reaction. All right. Now, this one is kind of the big scary one, right? It's bromine plus SO2 gives bromide and sulfate. And then it has in all caps, in bold, in base, and it's worth more points than the previous question. So, this is where you want to just be really clear in showing your work. So we've got to go through the full 8-step procedure here. And then the 8th step is the converting to base. That's the tricky one. So we break this into our two half equations like before. So I want to write down my two reactants. Leave a space, put an arrow, leave a space, put an arrow. Then I'm going to write down the products. There we go. It looks very kind of familiar, doesn't it? Then I'm going to balance for atoms that are not oxygen. So I'm going to need 2 of those, and I've only got 1 sulfur on the side there, so that's fine. And then I'm going to balance for oxygen by adding waters. So I'm going to add in 2 waters over here. And then I'm going to balance for hydrogen by adding H+. So I'm going to add 4 hydrogens over here. And then I'm going to balance for charge by adding electrons. So I'm going to put in 2 electrons there, and I'm going to put in 2 electrons there. And then what I'm going to do is if electrons gained doesn't equal electrons lost, I'm going to multiply one or both by a whole number so that I have equal number of electrons. But that's not needed in this case. So now I'm going to add these 2 guys together, cancelling where I can. And the first thing I try and cancel are my electrons. And so doing that, I end up with this guy. Which, if you're observant, is identical to what I had before. So some people picked up on that and other people didn't. So if you pick up on that, you're good. Now, the only difficulty here is that this guy has got 4 hydrogen ions present, and it says that it has to be in base. So what I've got to do now is I've got to add 1 hydroxide to either side for every H+, and then combine H pluses and OH minuses to make waters, and then finally cancel the waters. So I'm going to put 4 OH minus there, but I'm also going to put 4 OH minus over here. Then I'm going to combine these guys to make 4 waters, and then I'm going to cancel waters where I can. So all of these 2 waters is going to disappear, and then that's going to drop back to 2. So having done that, I'm going to rewrite my expression again. So it is Br2 plus 4 OH minus plus SO2 gives me 2 Br minus plus SO4 2 minus plus 2 H2O. So there we go. And if we check it, I'm feeling brave, I'll go ahead and do it. Bromines, 2 on the left and 2 on the right. Oxygens, 6 on the left and 4 plus another 2, 6 on the right. Hydrogens, 4 on the left and 4 on the right. Sulfurs, 1 on the left and 1 on the right. And there's only one thing left, is the charge. 4 on minus on the left, and then a 2 minus and a 2 minus gives me another 4 minus. So I got it, nailed it. All right, so I feel happy about that and I'm good to go. So again, that was kind of all over the place. That was sort of like people, if they had it, they had it. And if they didn't, they didn't. They were just kind of panicking and freaking out. But, you know, people can do it. You'll be able to do that. And if you practice, it's fun. Okay, I'm going to pause now on the video stuff. And I'm going to switch over to video of me. And I'm going to kind of try and make sure that we're all straight for what's going to happen tomorrow. So I will send out the normal announcement explaining how things are going to go down for the quiz tomorrow. And what we're going to do is I will send out that announcement after class. I already sent one out for my 162 class, and that'll explain the sections that are involved. And then a little bit before class starts tomorrow, I will send you a Canvas announcement with the quiz attached to it. You'll then spend all of class time working on the quiz, and I'll be available on chat if you have any questions. And then immediately after class, what I'm hoping that what I would like you to do is to scan that quiz, and then you'll upload it to Canvas, just like you have for your lab notebooks. Now, it's important that you try and do this, and that you, are able to do this successfully, because that's going to be the procedure that you're going to be using on Friday when it's time to take your final exam. So again, on Friday, what's going to happen at the beginning of the exam time, or a little bit before, so to give you a chance to get organized, I will send you an announcement with the document attached, and then you will answer the exam for, you'll have 2 hours to work on it, and then I'll give you another 30 minutes to scan that document and then upload it to Canvas. During the final exam time, just like during the quiz time, I'm going to be available on the voice chat, and on the, well, text chat is probably most appropriate. I'm going to be available to like answer any questions that you might have. Now, one thing that I want you to be aware of is when you're chatting during testing, or taking a quiz or the final, whatever it might be, you probably don't want to send a chat to everyone in the meeting. You probably want to click on the little triangle where it says to there, and then kind of scroll up and just select me, so that you're not sending it to everybody in the meeting and everybody's seeing your question. Okay, I mean, you can if you want to. I'm going to be keeping an eye on it, but just be aware that that if you want to send a message just to me, then you need to select my name. Is that okay? Are we all good? Is everyone happy? Do people understand what's going on? All right, at least one person does. So okay, cool. And Marissa, we might need to, I think you sent me an email this morning, maybe hopefully everything's kind of okay, that we've got arrangements worked out. But Marissa, if you've got anything that you need to speak to me about, just send me a text now, or send me an email or something, okay? All right, guys, well done. This is like what it sounds like it's going to be like for at least until April 24th. So yeah, okay.